Yeah. 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 This is backup, or is that the idea? Yeah. Okay. Okay. Test. Test.
Randy Calvert, I'm Themis Mission Operations Software.
I'm Joan Babonde. I'm Web Administrator for Mars Space Flight.
Sada Anwar, longtime software developer, Phil Christensen, and Tara Fisher, of course, and our guest of honor.
The old guy. Good morning. This will be, we'll keep it informal. I have a reasonable number of slides, which at my normal rate of about 30 minutes per slide would keep us here till March. But I'll try to go. They're somewhat in order. Feel free to ask us to go forward and backward. I'm going to distribute a handout. Why not? The top page of which is a brief index of all the slides with their number. So you could say, hey, let's go back to whatever number it was. And if we're lucky, you give Chris one. I don't know why. Randy, by the way, didn't complete his announcement of introduction. He's, as far as I know, he's the current KRC guru.
I got you here before I can call guru.
Actually, I'm just going to give you the whole stack and let him go.
I just want to make sure that no one falls asleep.
Okay, that's fine.
So actually, I'm going to keep interrupting. So we've segregated ourselves. Ex-graduate students along the back, software over on this side, young graduate students in this row. That's fine. That's good. I won't make you move. But one of the purposes here is, if there are 6 people from the software development team here, and I want them to really understand this model. So it's not just Randy trying to maintain it and support it. We're trying to put together websites, etc. So there's science users, new science users, software developers. The reason these guys are all here is because I want a body of people to understand the model and understand the software and how it all works. So Randy is one of several who I hope will be maintaining the KRC for a very long time.
Let me add a few. Well, we'll go back and forth between the slides, but I'm going to try to be completely informal. As you can tell by the color of my hair, I've been around a long time. And KRC started when I was still at Caltech. Chris, you're at Caltech now? My condolences. It started basically, and I can't even remember when, about the time I finished my PhD thesis, which was on Mars polar cap materials. And I got involved with some other people at the time who had instruments on the Mariner 6 and 7 spacecraft, one of which was an infrared radiometer, which had 2 little tiny sensors. They were co-located, so it was one spot, and they measured thermal emission at 10 and 20 micrometers, roughly. So you get 2 points in the black body curve. And they wanted to say, okay, what does it mean? And so I built a model that would say what kind of temperatures we expected, anticipating at the time the IRTM mission, because about then I got selected as a PI on the Viking mission, which was extraordinary bad judgment on NASA's part, but it worked out in the end. So at the age of about 27, I was a PI on a major Mars mission with an instrument that had 7 fields of view and could scan back and forth across the planet on the scan platform along with the other 2 remote sensing instruments. So I anticipated we're going to get temperature measurements all over Mars. That was the whole reason for doing this particular investigation. And we needed a thermal model that would support that. And so I built one, which at that time there weren't really none available. And I occasionally, one of the reasons that this little story is important is this development was done when computers were really slow compared to what they are today. And at that time, okay, first KRC. Let's get through the first slide. KRC stands for K, conductivity, R, the Greek letter rho, this normal symbol for density, and C, the normal symbol for specific heat. The square root of the product of those 3 is thermal inertia. And it turns out if you look at what is the result of putting a periodic boundary condition onto a surface with heat diffusion, which is what happens. Periodic boundary condition is the sun coming up and going down every day, and the heat, it heats the surface and it diffuses inward. It turns out that the solution for surface temperature doesn't depend on any one of these properties, but the product of the 3 of them. It's called thermal inertia. The larger the thermal inertia is, the more reluctant is a material to change temperature when you change the amount of power you're putting into its surface. And so I have no idea why I called it KRC, but I did. Also in those days, everything was done on punch cards. I'm a lousy typer, I still am. And so I tend to use short variable names. Another reason was at a time, you could only use 6 letters in a variable name in Fortran. There were a number of computing languages in those days. This is way before C and everything else you've ever heard of. I mean, the common languages were COBOL, ALGOL, and Fortran. And Fortran is, which stands for Formula Translator, was the language that was used for scientific computing. And though you may not realize it, it still is the primary language for really heavy-duty scientific computing. And so it has evolved with time. This was coded in Fortran 4, and it still pretty much is Fortran 4, even though there's been many generations of Fortran since. They're all backward compatible. And so one of the reasons you see really obscure names for variables is I was only allowed 6 characters, and I'm a lousy typist. At that time, I didn't anticipate that KRC was going to be used in as wide a range of applications as it has been. I built it for Mars. But at the time, we didn't even know where the North Pole of Mars was very accurately, because all we had was telescope observations from the Earth. So people knew, you know, it's about in that direction, give or take a couple of degrees. And so I wanted to be able to put in the right value when we got it. So hi Dale. Dale Noss.
Dale Noss and Mike Kraft also walked in. So,
Okay.
Good, you found the postdoc row. That's good.
So one of the aspects of KRC, which started from the beginning, was to keep as many of the physical constants input variables rather than firm coding or hard coding them into the program. And yes, sir.
Turns out we have 2 cameras recording you.
Oh, good God.
There's a web camera in the back, which we don't trust because it's brand new. That microphone goes to the web camera. So if you wouldn't mind. Thank you.
Turn it back on. I turned it off.
Yeah, you turn it on. Woo, woo.
Yeah. And do we have any idea why the screen is flashing?
It's having a hard time keeping the sync going.
I think it's going to drive us all.
I'm gonna look this way. Now we have feedback. Okay, we got to deal with the feedback.
Just turn down the mics, the speakers in the room.
Okay.
Right?
Yeah.
Over here. But,
Well, you should be over here.
but I need to be on the edge. It's a weird thing, sorry.
You could be right.
Okay. Anyway, we still have a fair. There, it seems it's getting less. Sadat will cure all. Okay. So there's a lot of. I mean, one of the reasons I'm going through this protracted introduction is one to get you in the right state of mind, which is pre-sleep, and also it's helpful to understand the nature of the program itself. So basically all the physical constants, everything that defines the environment that you're solving except the fundamental equation relationships is an input variable. And remembering when this thing started, you know, punch card days, the input is very highly structured. They're not in any particularly good order. The order of the input variables is more based on sequence in which I decided to code them rather than anything else. But they're all there on the front page at once, those of you. Is there anybody who has never looked at a KRC input file? Okay. All right, fair enough. We'll show you one in a while. But basically, the input file is a line of text, usually having 8 words, and below that, aligned with it, a line of numbers, which are the variables. And then another line of text and another line of numbers. So when you look at the input file, you can see where everything is. The problem is you don't know what it means. And that's the reason I distributed the stuff you have. The first page and a half are just the slide numbers. The rest of it is a thing called help list, which is a list I wrote to keep myself aware of what the whole thing was doing. And let me get my copy here because we're going to refer to help list a lot, and it will be your guide to find things. Starting at the at the bottom of page 2 is a line-by-line listing of the variable name and what it means. And first are all the floating point variables, then the integer variables, and then the logical variables. And so that's really the input to this thing. And all kinds of things are in there, including a fair number of parameters related to numerical convergence, which hopefully you will never have to touch. But those of you who plan on actually using this as a tool, or anyone who may consider writing a large numerical model themselves at some time in the future, hopefully in a different language, need to realize that the numbers you get out of these tools are no better than you put into them. And if you want to know how close to reality is the thing I'm computing, where reality is represented by the equations you put in, not the real world. I mean, the real world is something else. This thing models heat diffusion, and it omits a lot of physics that's actually going on Mars, but is hopefully relatively minor. But the fundamental character of a numerical model is you want to know how close do the numbers I get out represent the perfect solution to the ideal world I've created in my model. And this usually is, depending on what kind of numerical problem you're solving, it's a result of convergence and iteration and step size. And this is a numerical model. The numbers you get out depend on the step size, the number of times you converted things, what kinds of tests you have on things going out of bounds and so forth. And a lot of the complexity of KRC is tied up in the fact that all of those are input variables. Every one of them, with one exception. I'll get to there's like many numerical models, if you start to get toward the edge of stability, I don't know if this means If you guys have not had courses in numerical analysis or something like that, I may get out of your bounds. Feel free to ask a question. My wife will assert that I know everything. At least that's the appearance I give. So in this case, it's a good assumption to make. It's actually a pretty good approximation to one digit that for these topics that will come up, I know everything. Feel free to ask, and I'll feel free to try to tell you how confident I am of the answer. Numerical problems and numerical solutions are used a lot these days. Sylvain has run some huge ones. I don't know if you've coded any, but you've run some big ones. And the answers you get depend on how carefully you select the parameters you put in, including the convergence parameters. Now, occasionally I'll just step to the side and tell you a little side story. When I first developed KRC, I didn't know what convergence parameters to use. So in those days, the output was a page of printed numbers. We didn't have plotters. If I wanted to make a plot, I read the numbers of what I wanted the x and y axis to be, and I plotted them by hand. And so the start of KRC was trying to figure out, once I developed the scheme, which you'll see in a while, what do I use for convergence parameters? What do I test to say I'm close enough I can quit computing? And I did that by actually plotting these things by hand and looking at the results and thinking about it and trying another run, because a run was a one-day turnaround in those days also. Pick up your cards, you walk over to the building that has a computer in it, you give them the cards, they disappear through wall. A few hours later, you get your printout back. One run. Now, in that environment, supposing you had to write a big numerical model, one thing you try to do is make sure you could minimize the number of runs. And the other one is a corollary is, let's see if I can get the input parameters right. So I put a lot of thought in those days into just how KRC was set up. Some of those parameters are still there. They have been unaltered for nearly 5 decades. Feel free to experiment with them. In fact, I encourage you, if you're going to get serious about this, feel free to try to understand what these convergence parameters mean, change them a bit, and see what you get. And the variance of your answers will give you some idea of how confident you should be in the model. Now, I'm pretty confident that KRC is good to like 1/10 of a Kelvin for most of the runs you'll do. 1/10 of a Kelvin is way better than the answer is supported by knowing the physical conditions on Mars. So in that sense, KRC is good enough. And that's another side story. As a professor, I would say, don't believe the third significant digit without opening your eyes and looking outside the window. Try to realize or think about, how well do I know the input parameters? How well do I know the albedo? How well do I know the pressure, the elevation, the brightness of the sun, whether there are ice clouds around? How well do I know the slopes? What does my problem demand in terms of accuracy? And am I close enough? Okay, back to the slides. Now you can see why it takes days and days to get through a slide set when I'm talking. We have a new person. Would you care to introduce yourself?
Check to make sure you're recording all right.
Okay, I have no idea.
Rick is in charge of much, if not most, if not all, the technology in this building. So,
Ah,
That's his bad way to put it.
well,
Ignore me for a second.
the last 2 lines here are the required reading. Now, under Phil's encouragement and discipline, dominatrix would be a little too strong a term, I finally wrote this all up. And I am done with it. As of Friday of last week, I believe I've had my last interaction of any kind with JGR. And the final page proofs and corrections are through the system.
So what the previous version exactly had?
No.
So this has been 5 years in the making. So this is actually a very momentous some of it, all of us who reference this model reference a 1977 Kiefer et al. JGR paper that had 2
Appendix.
pages of model in the appendix. So we got sick of doing that, so thank you very much.
And
40 years.
it has changed a lot anyway. It's evolved. KRC, as with many, I guess, I mean, it's a statement I can't support, but I think a lot of models of this kind of complexity, they evolve with time. And it's still evolving. The fundamental numerical principles underlying it have only changed twice, which I'll mention later. But the actual, appearance and the little, what color the knob is and so forth, those may change a little bit. So anyway, this thing is available. All of you should have access to a version that's very close to the final version. At the end of the day, I'll talk to Siddhant and I'll put the final version, which has a few, numbers changed a bit, make it available to you.
Is it releasable? Can we put it on the site without
Well,
causing any issues?
I think so, but I'm not sure because it's a highly legal question. And those of you who have submitted papers recently may know the answer to this. But for instance, I just got 2 days ago a preprint from Than Putzig on, thermal modeling for Mars polar regions. And it's exactly what he submitted to the literature, to the journal. And I think as long as you say it's a preprint, you're okay. The current version which I'll put up there says informal copy, accepted by JGR down in the subprints, but it says informal copy all over it. And it's my version because the figures are all at the end rather than being stuck in the right places.
It's not formatted by GGR.
Yeah, as long as it's your formatted, it's your property, so yes.
Okay.
That version can go on the web,
Okay, but
and
it's
we
not
can do
considered
it.
as already published by way of being online.
No, and as soon as it's available online,
Well, it looks like JGR in one sense in that it's 2 columns and it has an abstract, but it doesn't have the JGR headers, it doesn't have the title lines, the figures and tables are all at the end. Okay. I think Phil got snookered into paying for open publishing. Did you?
yes, we did.
Okay. So hopefully it's done. Anyway, I don't know when it'll actually hit the physical stands. There's a preprint version which I could access. I'm not sure anybody else could access. But hopefully the open publishing version will be available in a matter of days. And that I attempt to describe this whole model. And in there I compare it with a few other models, everything from relatively simple models that are like the Joukowsky-Mellon model, which Than Putzig is still using, to an actual GCM with full up everything, which turns out to be a pretty lousy comparison because the GCM decided to use a model that was meters thick and didn't run it long enough for the meters and meters of material to reach equilibrium. And there's also in that article, there's references to a number of other thermal models people have built since this got started.
Ken, right?
Oh, yes. She's Datameister, right? Excuse me, I'm going to push a button, and we'll go see if it does anything. It does. So here's our goal for the day. Transfer the knowledge from me to you with 2 purposes. People who are going to maintain this thing and people who are going to use this thing. And I've tried to address both in this talk. I believe most serious users are going to want to install their own copy at some point because there are things you will probably find difficult to implement on the website, which can be done by KRC, but probably not with the web interface. I don't know yet. And I'm assuming that the people who maintain this are divided into 3 categories. A cognizant programmer who currently is I guess Randy, I'm not sure between Ken and Randy who's the cognizant programmer.
Well, I would put
There
that
will
in
be.
plurals.
Okay, that's fine, but
Because it's Randy, it's Dale, it's Ken, I mean, we're trying to spread it out such that,
so you ruin everybody.
that's one of the things we need to discuss.
Okay, we'll discuss it because
We do need I would like to have a single lead,
you have to have a lead programmer on
but on
this.
the other hand, people get busy and there's turnover
Okay.
and whatever, and so I don't want to just.
Well, I would imagine that we'll talk about this tomorrow, I guess. But there needs to be the role of cognizant programmer. There needs to be the role of mentor.
And when you say mentor, you mean somebody who knows KRC to the guts, understands it, or the model.
Maybe or maybe not. The mentor is the interface between the rest of the world and the guts of KRC. Now, whether the mentor goes to the cognizant programmer or the mentor goes to the code, that's up to them. But there should be one live body that a confused user can talk to for, just encouragement or something. It may or may not be a scientist.
And,
They need to understand the underlying science.
and we've had conversations, I don't want to, I think some of these roles are up for discussion. In my mind, Robin Ferguson has volunteered to be that person. The only downside to that is Robin is not physically here, but then neither is Josh, and neither is Sylvan, and neither is Edwards, and neither is
Me.
So-
And I am happy for the immediate future, I'll be the mentor. But my wife would insist on I have a plan on getting out of that role.
No, I
No, distance is going to be unimportant in this. Yep. So anyway, those roles, what I'm trying to do is to I want those people, some of whom or all of whom are here at the moment, a feel for what's going on. Because this is not an easy beast to deal with, to start with. I mean, it is not one routine. You can't just read the code from the top to the bottom. The last line is the standard codicil, or whatever it is. Disclaimer, which you should assume holds for every program you ever see, whether or not it's there. The documentation is the code. If there's a tricky question, the only way to be really sure is to look at the code or find somebody who can look at the code. Particularly in this case, because this thing has a long history. And I tried to document things, but not everything, and occasionally I may have made a change which had an implication I didn't recognize at the time. Okay. So we've already done the brief history of a long time. I could tell stories all day about stuff that your grandfathers understood. We will go over the physics that's included, and the one that's omitted, I don't know even the length of that list, because we don't know everything that's going on Mars. We'll go over the input format. There's two versions. There's two ways to run KRC. I forget why we implemented the one-point mode, but it's been handy. A lot of people have used it. Phil is, by total count, the biggest user, I'm sure. 1.5 billion cases, right? There's two modes, and I don't know a better terminology. We're going to call them the normal mode and the one-point mode. The normal mode is you do a run, it knows all about, you can change any of the input things. It's sensitive to all input parameters. The one-point mode uses a pre-canned set of input parameters plus a few numbers that you may change. And that's it. But you can run lots and lots of those. You can have lots and lots of lines of those numbers.
Are you going to come back and talk more about those two?
Yes,
I think
yes.
I think there's a fair amount of confusion between them. So
Okay, we'll talk about this in some detail.
Okay.
Case. The whole Viking mission was run on 3 cases because that's all I could afford. I didn't mean an hour. I took over the university's entire computing facilities for an hour, all of them. Imagine going to ASU shutting everybody down for an hour. That's what it took to do one case. The scheme is implicit forward differences, and I need to talk about this a little bit. There are lots of ways to model numerically the real world. One of the simplest ones is this, where you imagine in the physical dimension of your model, in this case depth, you have the results by some miracle for some time. You want to know what happens in the future. Well, you take these three and do a little formula, and it predicts the center one in the future. This is called explicit forward differences. Again, if you've had a case in numerical analysis, you've probably come across this. This is the scheme that KRC uses. There are many other schemes. This one has the advantage of being very fast. It has a different disadvantage of being unstable under certain conditions. If you make this jump too small, if you make this jump too big compared to these, it doesn't really know what to do. And there's physics behind this. Imagine that you have you're in a material where this represents time and heat's diffusing forward in time. That's what heat diffusion does. If you ask it to jump forward in time greater than the length that natural heat would diffuse, you're asking the mathematics to do something the physics can't do. And it goes numerically wild. So the constraint on KRC, and we'll come to this later, there is a constraint relating the steps in time versus the steps in distance under which this thing is stable. And you want to actually work sort of right up against that boundary of stability. If you go beyond it, you get wild results. If you stay well within it, you're just taking more time than you need to do computer. You're taking more iterations than are necessary. So I chose, this should say explicit forward differences. I believe, I don't even remember. Anyway, it's forward differences. And that's the scheme. I carefully coded for speed, and it is evolved. And there have been basically two major changes in the history of this routine. The first is I went to a physics-based one-layer atmosphere. When this thing started, I made the assumption that the radiation coming out of the atmosphere down onto the surface was 1% of the noon solar flux. I didn't know what else to do. And this was before this first spacecraft had gotten to Mars, basically. So that's what I assumed. And it ran that way for years. And then sometime, and it says in the code actually when, I went to a physics-based atmosphere that actually scatters radiation and has it has heat, and it can cool and get warm and so forth. And that a lot of the complexity in KRC actually is in that. Output formats are a minor issue. And then a few years ago, I went in and allowed temperature-dependent physical properties, which is what the real Mars is. The specific heat and the thermal conductivity of materials do depend on temperature. Not terribly strongly, it turns out. It also turns out they are sort of in the opposite sign, so they somewhat cancel. So it isn't a big issue. But we didn't know how big an issue it was until we actually ran some models. And there's some more history. The primary results from the Viking mission, which was the first thing that really looked at temperatures through the day on Mars, there's a feature which we call anomalous afternoon cooling. Afternoon, the temperatures on Mars drop more quickly than you would expect from these models, from any member of these models. There are places on Mars where it just cools too quickly. And people tried for 20 years to figure out what that meant. And we may finally have an answer, which has only been in the literature for the last year, which is katabatic winds. Katabatic winds are winds that flow along different temperature surfaces, particularly the strong ones in the Earth. We get really cold surfaces, Cold surface cools the air, it gets denser, it flows downhill, more air comes, turbulent mixing. You get strong winds, particularly downhill in the afternoon as surfaces cool. And it maybe that's what's doing this stuff on Mars. Though this is a relatively young suggestion and it hasn't been thoroughly evaluated. Okay, finally something worthwhile listening to. KRC allows you to have the term layers is used here in two senses. KRC divides the subsurface into a set of layers. And those layers can be of two families of materials. The top end layers can be of one material, and then all the rest can be of a second material. And each of those materials can have its own conductivity, density, and specific heat. And they may be temperature dependent. There's a switch. KRC has a single switch. If you set this switch false, it ignores everything that has to do with temperature dependence, and it runs twice as fast. Yep.
Going back to your changes, so that changes in the last handful of years?
Yeah, like 4.
And going to the one layer atmosphere from the 2% downwelling, was that between Viking and TESS, or was that post-TESS? I'm trying to think of what the thermal maps of TESS were done with as far as atmospheres.
I can look it up.
I think it was pre-test,
It actually says,
because I've never used KFC without the fancy atmosphere.
Okay.
So it could have been much past test.
I believe it's in the first page of the help list.
Well, there's two. You had a one-layer atmosphere and you had a Delta Eddington atmosphere. Are those the same thing?
This says 2002, July 12th to 17th. Replace atmosphere with a Delta Eddington model.
But before that, so
Before that, I had
was it the 2% downwelling?
1%, or what? It was X percent. You could
Right.
set it was normally
So
1.
you basically just had X% of the noontime radiance
Down all the time, constant.
or a one-layer Delta Eddington atmosphere.
I
Or is there 2 steps in there?
I don't recall. I don't recall doing anything with it's a one-layer atmosphere. It's 2-stream.
Right. One layer, 2-stream, Delta Eddington.
For those of you who don't, okay, this is a good place to take us. We'll come back to this. We'll come back to it.
Okay.
What a Delta Eddington atmosphere is.
For historical reasons, I'd like to at some point say IRTM was done with the fixed downwelling.
Yep.
TESS was done with X. Themis was done with Y.
Well, TESS was done with Mellon-Joukowsky,
Right. And
which is a conductive radiative atmosphere, far more complicated atmosphere than this. Not much difference in the result, but way more complicated atmosphere, and it takes a week to do the runs.
Right. But then you added the Delta Eddington as an improvement to the Ames, Pollock, weird atmosphere that was used for TESS.
Yeah, there's a reason why he's using the term weird. Again, history, it's in the paper, which you probably haven't read yet, but there was a fellow named Jim Pollock who was an atmospheric scientist working with Mars. He was a bright guy. And the model atmosphere that was used during Viking and for the next 2.5 decades was based on his model of the atmosphere, where he pre-computed all the scattering phenomena and made a table of them that says these are the parameters you use for atmospheric scattering on Mars. And unfortunately, Jim died. And Mellon-Joukowsky model still uses these parameters. And as far as I can tell, nobody knows how he did it or where they came from. They just use them. And Putzik and Mellon have talked about redoing this. Do you know if they have? I don't know if anybody has actually redone what would now be straightforward calculations to generate the model. So anyway, there's another model out there. The TESS mission used Joukowsky-Mellon calculations, which Mike and I went over in advance. We chose the parameters and how the runs were going to be done, and Mike ran them. I wrote the interpolation code. And I believe that's what the test production model was. The Themis production uses KRC models. Okay. Here, the rest of this list is basically why KRC is complex. The two parameters, density is not a strong function of temperature. It does change with temperature, but it's tiny. You can just take the linear coefficient of expansion and cube it to get the volume, in which they're typically like 10 to the minus 6. It's tiny. You don't worry about it. Specific heat and conductivity vary. Conductivity particularly can be a very strong function of temperature on an airless body with fine particles like asteroids and the moon, because there's a radiation component which goes as t to the t cubed. And that's one of the reasons I chose to model temperature-dependent properties with a cubic equation. It's not really needed for most cases on Mars. A linear would be just fine in terms of the magnitude of changes. But because I wanted to be able to address airless bodies, and because it's easier to do the same thing twice, we use cubic equations to model these things. The next one is one that many models do not have. The terrain can slope, or it can be in the bottom of a pit or crater, if you wish. Now, I won't, I'll try to remind me to go into more detail on this later, because again, it's a first order approximation to things. It's not a two-dimensional or three-dimensional model. The lower boundary can be either insulating, which means no, or called adiabatic, no heat flows through the lower boundary, or it can be a fixed temperature. Both of these can be dramatically handy depending on what problem you're trying to solve. And both of them, I use both of them a fair bit. Again, it can be any orbit, spin axis, rotation period. The one-layer atmosphere, it's one layer, but it has two spectral regions. It has solar and it has thermal. The way those are handled is different. The reason is that most thermal radiation is isotropic, means it radiates the same in all directions. And solar radiation is only on days like today close to isotropic. Normally it's very directional. And the way the atmosphere treats this, the way I treat it are different. And we'll come into that. The visible part, the solar part of the spectrum is done with a two-stream delta Eddington. The thermal part of the radiation is simply assuming that it's isotropic everywhere, that radiates the same in all directions, which is probably plenty good. Josh? Josh? I should say there are expertise here that you should use when you get a chance. Joss is an expert in the atmospheric aspects of this stuff. Robin is an expert in the surface, in the real surface, grind your wheels in the soil of this stuff. Sylvain is an expert in the relationship between conductivity and particle size and pressure and welding and cements and so forth. So you got three experts back here. Chris, I'm sorry, I don't know what you... Pardon? Okay. But there are people back here who know more about some of these things than I do. So use them. So we have atmospheric radiation, but no conduction between the atmosphere and the surface. The atmosphere itself is assumed perfectly conducting. That is, the whole atmosphere layer is one temperature at any given time. It changes with time, but at any one time, the entire atmosphere is assumed to be the same temperature. A very bad approximation to the real Mars.
What about modeling for something like type? Is it applicable at all?
Well, I can't really answer that question. I can tell you what KRC models. And you'd have to decide whether or not, yes, Titan is close enough to that. The critical number here would be the opacity of the atmosphere. If the opacity of Titan's atmosphere is small, so radiation, a lot of it gets through, and so then you could probably use this kind of an approximation. The delta Eddington will work fine for an opaque atmosphere. The assumption that I make in the thermal would not. The assumption I make in the thermal is that the temperatures, the radiation is coming from this layer, and everything that it sees from the bottom is the same temperature. And if the opacity is high, that is not true for an atmosphere. It's going to see the bottom temperature at the bottom and the stratospheric, thermosphere, whatever it is at the top. And it's not going to work too well. Good question. It does conserve energy. That's the thing that governs the atmospheric temperature, is how much energy gets stuck in it as the radiation tries to get through. Another aspect, and this is peculiar from, the incentive was Mars, is that it actually checks to see whether the atmosphere gets cold enough to condense. And this is not suitable for the Earth because the thing that condenses on the Earth is a minor component. On Mars and Titan, the thing that condenses is the primary component of the atmosphere. And so a lot of physics goes on that doesn't occur on Earth. The analogy for the Earth would be getting below 77 Kelvin. And nitrogen starts to drain out of the atmosphere and fall on you. It would be very uncomfortable. The terrestrial equivalent to Mars doesn't occur. But this atmosphere does worry about it getting cold enough for the primary gas to condense, and I assume it's going to fall out like snow. There's good evidence that it does this. Mars grows polar caps every year. So my atmosphere worries about that and takes care of the transport of energy from the atmosphere to the ground as snowfall. And then once it's on the ground, it takes care of the fact that now we have a different boundary condition. The temperature can't go up and down anymore. It's stuck at the snow temperature. And that condition, the boundary condition of being stuck at the snow temperature, holds until you get enough energy down there to sublime, melt the snow away, and you go back to having a dry surface. So this model handles that. And so that's what's in the next few lines here. Okay, so it falls as snow, if the surface gets to the CO2 condensation temperature, whether or not the atmosphere has, it also starts to condense snow on the surface physically. And Mars does this in spades in wonderfully complex ways that we won't get into here today, but just say it's amazingly complex. Randy?
So on Mars, things condense as a solid, but would liquid change this? Like hypothetically, if something condenses a liquid,
No.
Is the liquid as it flows, would that change the temperature behavior of that layer?
Yep. I'll tell you what the model does, and then and then we'll quickly go through the model has two ways that it can be in a, quote, frost condition. And actually gets triggered by the surface temperature itself getting cold enough for frost. And when that happens, I stop I change boundary conditions. I change from this equilibrium, you'll see the equations, energy condition, I change to fixed temperature. If there's any energy left over, it goes into changing the mass of the frost. Either it grows or sublimes. Now, if the atmosphere gets cold before the surface does, which rarely happens on Mars, but if it does, the snow falls, but it gets to a boundary condition that says I don't have any snow, and rather than trigger things, which would be really complex, the energy just disappears. It's a non-physical treatment. So if you have a freezing atmosphere and a warm surface, KRC ignores the surface part of it. If you have a cold surface, the energy gets added and treated appropriately. Now, I'm not done with him quite yet. If you had a liquid and the surface was parallel to the geoid, i.e. level and no flow, it would work just fine. The physics would be fine. If you have a surface with swales and dumps and things, you're going to get lakes here and dry there. Doesn't handle that. Phil.
So I want to come back. So it condenses in the atmosphere, and so you're worrying about latent heat and all that stuff. Okay, so you're taking energy out of the atmosphere.
Right.
But you're saying it doesn't get transferred to the surface. It just kind of goes away. So the atmosphere
that is true when the atmosphere is freezing and the surface is not. A condition I have found in running models, and I mentioned this in the paper, to occur only briefly at the edge of the North Polar Cap. The condition's gone in a day. And that amount of, actually one of the reviewers caught this, and you probably haven't read it post-formal review. I wouldn't expect you to have wasted your time doing that, but one of the reviewers caught this, and so I actually calculated the worst case, and it's equivalent to changing the atmosphere temperature by about 2.5 degrees. That's the very worst case, and it only occurs in those circumstances. The other thing that KRC does is this, gradual for albedo. Realistically, when snow falls on the ground, it doesn't immediately become completely white. It's, gradually dark. It depends on the nature of the snow and how much there is and so forth. KRC handles this. It actually there's two parameters that govern the smoothness and the length of the transition between dry soil and completely opaque snow. So there's a couple parameters that allow you to handle that. Okay, and the total frost, this is another thing which KRC will do if you care. And occasionally, because I worked on the polar caps, I did care. It will keep an inventory of how much snowfall is on the ground, total up the mass over the whole planet, subtract that out of the atmospheric mass, and adjust the planetary surface temperature, which is just what occurs on Mars.
Surface pressure.
Surface pressure, sorry. Yes, surface pressure. It adjusts. And so and on Mars, this is a big effect. On Earth, it's completely negligible. But on Mars, it's 25% of the atmospheric pressure every year. About 40% of the atmosphere condenses one place or the other every year. Or you can use the known pressure relation measured by Viking and maybe updated by MSL, we'll see. Or you can just have it constant. You choose. All three conditions are handled. This is something I added and I don't let anybody abuse very much. You can use a table-driven, and I should have stuck the word global in here. You can have a table-driven opacity and surface albedo that are applied to all latitudes that you're running at that time. But you can put this table in and you can have as much detail in it as you want. It does linear interpolation between all the points you give it.
Can I go back one? So if you use the Viking Lander relationship for pressure, it doesn't go backwards and say, hold on, you can't have that much mass condensing or the pressure. You basically let the mass do what it does in terms of growing polar caps, but you let the atmosphere just track what the Viking landers measured in terms of pressure. Or, see what I'm saying?
Yeah, I think, let me see what you triggered something. What I think, I'll tell you what I think it does. If you set the pressure constant, because it actually looks up the saturation pressure and temperature at one scale height above the local surface, the actual physics for when snow falls on Mars depends on the actual elevation and the atmospheric temperature and the surface elevation, and not the temperature. And that will condense and fall out. If you set the pressure to be constant, then the pressure it uses for the atmosphere will be constant all year long. And if snow falls out, the mass of the planet numerically will actually grow in this case, because you're adding mass to the surface and you're not taking it out of the atmosphere. You take the energy out, but you don't take the mass out. Okay. So back to this line. So you can have table-driven opacity and albedo, and this is handy because Mars surface albedo just changed through the year. And if you want to see what would a place do if I got brighter in the spring and darker in the fall, you can handle that. And these are separate. There are two separate tables for these two. Another thing I've added recently is the ability to use a map of dust and ice opacity. And this is a zonal map. It says how much dust clouds do I have and how much ice clouds do I have as a function of latitude, as a function of season. And is currently firm coded to be 5-degree resolution in latitude and 5-degree resolution in season, and linearly interpolate between those. And the actual file, which is available for you to use, is one that I derived from Mike Smith's Themis maps by taking all his years and basically averaging the independent years. Yes, John?
What number do you put in where there's no data?
I've forgotten, but it says in the paper. Okay. Within the temperate regions, it does a filling algorithm. Sure. At the poles, I put in some low-no numbers, like part 1,000, 001 for probably for both these. Okay. The poles, another thing, okay, for those of you not familiar with Mars, this is a huge approximation for the polar regions because the poles act very differently. The North Pole develops this huge, what's called polar hood. Basically, it's like high clouds all winter long. The South Pole remains largely clear. And I have artificially faked it as a clear case. Hey, Robin.
Try to split yourself with water, ice, and dust simultaneously.
I allow them to be separate. That's right. They're actually, KRC now has two opacities for the solar region. One for dust, which assumes uniform mixing, so the opacity scales with column pressure. And one for ice, which is assumed to be a cirrus level and does not scale with pressure. I use a two-stream delta Eddington, and I think I go in and combine those two to get the effective albedo for the Eddington layer at that time. And I only have one set of scattering properties. I use the dust scattering properties. There's only one Henye-Greenstein parameter. Okay? That's the Henye-Greenstein parameter we'll get to. Don't worry about it. Any more? I mean, there's nobody. Just... Josh?
I don't know.
Because then you could take into account both the dust scattering properties and the water scattering properties separately. And
Yeah.
would that be a more accurate?
And I'm not sure I'd use a 4-stream or 2 parallel 2 streams. I don't know the right answer to this. You got the world's expert on your left here. Or you got somebody who knows a lot more about this than I do. And I mean, I encourage you all, to encourage everyone here, if you see something that should be considered as an addition, write it down so you don't forget it. And we'll keep a set of liens.
A question I have is for the meeting is how much are we going to be talking about future development? And the atmosphere is an obvious one.
Mm-hmm.
And one other thing I was going to mention is, like, for the lunar stuff, we're no longer doing upper and lower. We're doing constantly changing properties with depth.
Yep.
So are those things that we can plausibly discuss?
Sure.
Sometime the next day?
We can discuss how much effort we put into them. I'd say make the list and make sure the list doesn't get lost, and then we can go over it. These two problems are nice in that they are separable. And I don't know how complicated the first one is. Probably not terribly. The thing is, I mean, I call a subroutine figure out what the atmosphere does. And if we just called a different subroutine, that would be having continuously variable parameters with depth would have years ago been a huge impact, but not any longer, because I've coded for things changing with depth already. Now to change, I mean, the only thing left is density, which would be easy to code for, and variable layer thickness, which would be a different set of equations.
So one of the things that, you know, I still have this little drawing on a Post-it that's stuck to my bulletin board. You know, if you go back, you know, there's the Mellon model kind of spun off, and the Joukowsky model and the Putzig model derived out of those. Mark Richardson is divided, and Dave Page.
By the way, this isn't my